Hello, welcome to our next section in Unit 2. We're starting Chapter 6. We're going to start with talking about characterizing data. We're going to look at data sets and the way we kind of measure and try and understand data sets. First off, when we talk about data sets, we usually talk about distributions. The distribution of a variable or data set is the way its values are spread over all possible values. We like to show distributions with tables, with graphs. So when we go out and we do our survey, we collect data, we look at how many people have these different colored eyes or maybe some other kind of set of data. We can visualize that, making those bar charts, histograms that we talked about in the last section, making tables of values. There are lots of components to the shape of the data though, so after we're going to go through in this section, we're going to talk about the different things. One of the big things we look at is the center. So the center of data set, also thought of as the average. You can think of that as kind of the typical value or the value in the middle. There's actually lots of different ways to measure that, but that's useful information. It's good to know like what's typical, what's average. When I think of this group of data, what's going to be most common, what's going to typify the set. So some of the big measures we use are mean, median, and mode. You've probably seen these before. Hopefully these are not new to you. Mean, you've seen as average. A lot of times when people talk about average, they're talking about the mean. So the mean, most common called the average, it's just the sum of all the values divided by how many values there are. We usually use n for the number of values. So you add up all the values, divide by how many there are, and it gives you a way to measure the center. You find the average. Next one is median. There are times when median is actually a better measure of center than mean is. There's certain times you do it. So median is the middle value. You basically just find what number is in the middle, but it's important to make sure your data is sorted. I used to teach like 7th and 8th graders, and they would be learning about median, and I'd have so many of them that tell me the median was this random number that ended up being like the top number in the set. Well, it's because they gave them the data not sorted, and they didn't sort it. So they just picked whatever number was in the middle, even though it happened to be the biggest number in the set. That doesn't make any sense. If you're trying to find the middle number, that data has to be in order. If there's an even number of values, you won't have an exact middle number. In that case, you just take whatever, you find halfway between the two middle numbers. So if like 6 and 8 were in the middle, then 7 is halfway between 6 and 8. 7 would be your median. So it is possible median to be not a number in your set if you have an even set and you're just averaging those two middle numbers. Mode is the most common. So you just look for what number showed up the most often. So the most common value. A lot of times mode doesn't make any sense, not very useful, especially in example problems we're going to do, because when you only have 5, 10, 15 numbers, a lot of times you don't have more than one of a number, and if you do, it's just some random value that end up having two of. So mode is not useful for small sets of data. When we start getting to real life situations where you collected maybe hundreds, if not thousands of results, then mode ends up being really useful, because if something's showing up more than anything else, it's showing up a lot, it's showing up hundreds of times, 1,000, then it actually means something, and it's actually going to be kind of typical for the set. So mode is really useful for large sets, for actual data sets, and sometimes we really like mode. It is possible for all the numbers to only occur once, and that would be when you don't have any mode. It's also possible for you to have more than one number shows up the most number of times. So maybe 5 shows up 10 times and 6 shows up 10 times. They both show up 10 times. And then 5 and 6 would both be your modes. So you could have more than one mode. You can have no mode. Those are all options. There are actually lots of other measures for center. We're not going to cover these other ones because they're not as commonly used, or they're used in more advanced statistics that we're going to do. But mid-range, geometric mean, harmonic mean, trimmed mean, min-mean, these are all ways to measure center. So there's not just one measure of center. A lot of times people think of average as just one number, but any number you use to measure average is just one way of thinking about the middle. What's the average? What's typical? And they're going to have better times where one measure is better than the other. There are actually some data sets where they're all the same, so it doesn't matter which one you pick because you get the same for all of them. Sometimes they're different. That can really depend on the data set you're working with. So part of statistics, if you go into more advanced study of statistics, is actually determining which measure do you need to use, why are you using it, and how to use it correctly. All right, so here's some data. We're going to find mean, median, mode. That's what most of the homework for this section will be, is just finding mean, median, modes. That's most of it. So below the prices of board games are listed. Describe the distribution of this data, giving its mean, median, and mode for the prices. So first, we'll start off with mean. In order to find mean, you have to find the sum, and divide it by the number of values. So that's what mean is. We first just need to add up all those values. That's my phone, not my calculator. First, we need to add up all the values. Kind of fun part about statistics is a lot of times it's just sitting here adding up, doing kind of simple calculations with lots of numbers. And we're doing small data sets. Like in real life, our data sets get even bigger. That's why it's nice to have computers and programs. Excel will do a lot of statistics for you if you get handy with Excel. But yeah, okay, we have 232 is our total. And I had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 values in my data set. So again, N is your sample size. It's, when you go and do your survey, you went out and checked prices, win board games. That's the count of how many you looked at, how many values you have. I just divide it, 232 divided by 11. And so I got 21.09, repeating. So I'm going to just round that up to 21.09. My math lab would specify for decimals like this how long to round it. So it'll give you 1, 2, 3 decimal places depending on the situation. I just went 2 decimal places on this one. That's mean. Median, well, you can't do median unless they're in order. Before I do median, I'm going to have to sit here and write these numbers in order. So first off, I notice that 10 is the smallest number. I think then 15 is next. Yeah, 15. I actually have more than one of those. There's one over here. And there's one over there. There's 17. Looks like 20 is next. And another 20. 25. 25. 34 is next. And then 36. We got them all. There are ways to find the middle of the set of data like this, but I'm just going to use the good old grade school method of just cover up. So I'm going to put a finger there, and I'm just going to go in one on each side at the same time until I found the number that's in the middle. If you did it right, there should be the same number on each side, right? So I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That number is the middle, and that's the median. So the median for this set is 20. And that's median. Median, as long as you have an order, it's not too big a deal. You just have to find that middle number. Again, this was an odd set. There was 11 values, so there was one middle number. The next one I'll show you one where it's even. You have to find the average of the middle two numbers to get the median. And then mode. Mode is just the most common. So just look for what shows up, multiple times. And here, now that they're ordered, it's really easy to see that there's 3 15s. So 15 is the mode. We can see that's the most common. And you can see there's a lot of difference, between mean, median, and mode. Mean and median are fairly close together, 20, 21, but they're a little different. They're not the exact same. So that's why sometimes someone might use mean versus median. If you're trying to make the data look, one way or the other, you might pick the one that, matches if you're trying to just show it off. If you're doing, actual, rigorous statistics, you'll pick the one that's most appropriate for the situation. You'll look at conditions of the data, and then decide which one is usable. And then mode, you'll notice, is way far away. 15 is not anywhere close to 20, 21. And it's because it's a small set of data. Like I mentioned before, you have a small set of data like this, only 11 values. It's possible for one random number to show up a lot. So 15 is fairly common. It shows up 3 times, but it doesn't mean it's that much better of an example than 20 or 25. They're only, there's 2 versus 3. So it's probably not great for the whole set, as a representative. Yeah, there's 3 out of 11 that are 15s, but it's not the best measure of center, maybe. According to extern.com, these are the pay rates of the 10 best paying bachelor's degrees in 2024. Give the mean, median, mode for the salaries in thousands. So these are the top 10. I had to shorten the titles a little bit. Some of these are combined majors, but here's the top 10, rounded to the nearest thousand. So the petroleum engineering make 187,000, industrial engineering 170,000. A lot of those engineering jobs at the top, 159,000 for electrical, interaction design 155, public accounting 148, operations research 147, applied economics 146, business computing 143, actuarial mathematics 143, and electrical power engineering 142. And these are again in the thousands. So we want to find mean, median, mode. Again, to find mean, we have to add them all up and divide by how many there are. So we're first going to have to add up the numbers. So add those up. So I get 187 plus 170 plus 159 plus 55 plus 148 plus 147 plus 146 plus 143 plus 143 plus 142. And that gives us 1540. Hopefully I typed that all in there correctly. And here I have 2, 4, 6, 8, 10 majors. I guess I put that right there. There's 10 of them. Just divide by that 10. So here I actually have 154,000 is the average salary for these. And there's people making way more after day 7. People making somewhat less at 142. But this is kind of your typical average. So that'd be the kind of middle. And if you look at the middle, you'll see that you get a little bit difference. When we do median, you'll see there's actually a bit of a difference. But yeah, thankfully these are in order. If you notice, I'm going, there's the top and the next, and they do work through order. So I'm going to do cover up still. I'm going to start with the bottom and the top, and then covering up as I go. So just continuing to cover bottom and top, and I see that these two are the middle values. So to find the median, what I do is I have to find the average of those two values. So I'm going to take 148 plus 147. I think those two values just divide by 2. That's how you can find the middle of any two numbers. Just add them up, divide by 2. It's average that we think of just averaging two numbers. Of course, 148 plus 147 divided by 2 is going to give us halfway between, which is 147.5. If you know that, if you just know that 147.5 is halfway between these two, you can just do it that way. But if you don't know what the average is, you can always do that trick of just adding the two numbers and dividing by 2. So when there's 2 in the middle, this is an even set, 10 values. When there's two numbers that are kind of in the middle, then you just find the number that's halfway between those two. Last, we have mode. Again, mode is just what happens most often. So do any of these numbers repeat? So 142, 140, oh, there's two 143s, 146, 7, 8, 5. The only two that repeat are the 143s. So 143 is the mode. Again, small data set, 10 values. Mode isn't really meaningful here. It's on the low end, right? You can see how much smaller it is than the other two. It's still not terrible, because it's at least within 11 of the mean and within 5 of the median, but it's not a great way to measure center with a small set of data. Again, if I had looked at 1,000 majors, mode would probably be a really good way to look at what's the middle, what's typical, but not with just 10. So those are the 3 ways to measure. Which way you use can really determine what your result gets. So if you're trying to be a little deceptive with your statistics, you pick one that makes it look a different way than maybe it is. Or if you're just trying to be accurate, you kind of think about which one's the best measure. So let's talk a little bit about what makes one the best measures. We have to talk about something called outliers. So there's an interesting story that the textbook had. I'd like to share it. So a survey once found that geography majors at the University of North Carolina had a much higher average starting salary than same majors from other universities. So this big company was looking and said, okay, where do you want to get your geography major? And they looked at the data and said, wow, if you go to UNC, you can have a way higher starting salary. The average starting salary is so much higher from there. Well, then, they looked a little bit closer to the data and realized that they had one salary that was so large that it kind of blew it all out of the water. It just destroyed the average. It was because UNC, that's where, Michael Jordan graduated back in the day from UNC, started, instead of going on to, teach geography or something like that, he went on to play basketball, of course, and made millions. But he did have a geography major. That's what he studied was at school. So his salary would be an outlier. It's a value in your data set that is much higher or much lower than other values in the data set. You can at most have 2 outliers. You can have one at the top and the bottom. You're not typically having more than that. If you have a couple values that are really high at the top compared to everything else, you might consider them both being an outlier. That could happen. It depends on the data you're looking with in your situation, how much you have to worry about outliers and stuff. But usually, you're going to have one on the top, maybe, or one on the bottom. No, you maybe both, but not very often. So it's one value that's much higher, much lower. So much higher or much lower than all other values. So Michael Jordan's salary is way higher than everybody else's. It doesn't have to be high, though. It could be very low. You can have the one geography major that got a job working a really low wage, just, in a job because they couldn't find a job with their geography major or because they didn't want to. They decided to hate geography and went and got a part-time job. something low wage, they could be an outlier on the bottom. That could happen too. So for example, the times given here are from one of the heats of the 100-meter dash at the 1960 Olympics, which value could be considered an outlier. And then we'll look at how that affects the median and the mean. So right here you can see that almost all these are in the 10 point something seconds, 10.2, 10.8. Those are all really close together. Of course, the one that's different is the 8.4, because it's way faster. It's like almost 2 seconds faster than the rest. There's a 0.6 spread here. There is a 1.8 spread here. That's 3 times the spread between these two than there is between those two. So this is way lower. So this is definitely your outlier. Anything that's way different than the rest. This is a big difference. Now let's look at what happens with mean and median. So first off, look at mean. So mean with all the values. So let's look at what we get if we add up all the values and find the mean. So I'm going to add these values. I have 8.4 plus 10.2 plus 10.4 10.4 5 plus 10.8. So add this up, I get 60.7 over 1, 2, 3, 4, 5, 6 values. So divide that over 6. And we get 10. So 10.11, I'm going to put 10.1. If I do the same thing, but now I take out the outlier. So now instead of adding all those, I'm going to add everything else. I'm going to go up there, hit enter, and zoom over here, delete the 8.4, add everything else. So without, I have 52.3 over 5 values now because I got rid of that 6th number. So 52.3 divided by 5, I get 10.4, or 10.5 to be rounded. So 10.5. That's a good 0.4 change. That changes significantly just by removing this one value, because that 0.4 is almost the difference between. It's the difference between being below all these ones and being here in the up here on this side. We move from here to here, that location, by just adding that one number. Now, if we look at median, let's look at median. So if median, if I do the cover-up method with all of them, and with 2 numbers in the middle, well, it's 10.4 on both of those. So the average of 10.4 and 10.4 is 10.4, so the median is 10.4. And if I take out this 8.4 and I look at these guys, and I cover up, I go, cover, cover, I end up with 10.4 in the middle still. So 10.4 either way. It doesn't matter whether you have that number in there or not. Because it's just a number out on the end like this, it's not going to significantly change your answer. Because you covered up, it doesn't matter if this was 10.1 or 8.4, it's the first number I cover up. So medians don't really get messed up by these outliers, and neither do, but means do. Means really get changed. Notice also that mode would not have been affected, because mode would have been 10.4 either way. You take this number out, put it in. It's not the most common because it's an outlier. So 10.4 would be the mode either way. So mode is actually also 10.4 either way. So we call this resistance. We say a measure that's not strongly affected by outliers is resistant. So mean would be the one that's not. Mode and median are definitely resistant. So median and mode are resistant. So one time when you would not want to use mean, and you would definitely want to try and work with median or mode, is if you have outliers. So if you look at your data set and you go, oh, well, there's going to be some values that are going to be much higher than the rest, or some values that might be much lower than the rest, then you have outliers. So here we have race times. You have one person that was way better, kind of just the one racer who's so much better than everybody else. Took away, easy golds. Kind of you Usain Bolt or Michael Phelps, someone like that who just kind of broke a bunch of records and just outclassed everybody else in their races. That would be an outlier, and that would destroy your mean, making your mean not a very good measure because of the outlier. Another thing that can happen where you can get outliers, if you're in science and you're doing like labs and studies, if you've been in like biology or chemistry class and you're doing your labs, and you have your data you collect, and one data value is way different than the rest, you know that sometimes what happens is you don't do the procedure properly. You make a mistake. You boil it too long. You contaminate your sample. Something happens. That's where a lot of outliers come from. So a lot of times when we're doing statistical analysis of data collected, of lab reports and stuff like that, they'll look for those outliers and try and decide maybe was there something that happened that made that value not useful, that made it an outlier. That's something we look for. Is there a reason that's an outlier? Is it because of faulty data? And if you can determine it's faulty data, then you probably remove it and try and get rid of it and try not to work with it. But you can't always determine something's an outlier. Sometimes you're stuck working with it. So outliers you got to watch for. They really change how you work with data. And again, mean is not good with outliers. Median and mode work great with outliers, but not mean. Okay, let's talk more about shapes. So this data, we talked about how you can graph it in the histogram. You can look at the visual shape of it. And the shape of the data can actually tell you a lot about the data just by looking at the shape. It's amazing how much you can adjust for the shape. So if we create a histogram or a line graph, you get a nice visual. Here I've got line graphs, but you could have made these kind of same ideas with histograms. Then you can observe some of the different shapes. And you notice that here we have different amount of peaks on these. So the peaks, the number of peaks is called the modality because it actually refers to how many modes you have. So if your data has one mode, if you look and there's one thing that's more common than the rest, that would be unimodal or a single mode, that would be one peak. So anytime your data has one thing that's the most common, one thing that's kind of typical for the whole set, that's going to be your single mode. It is possible to have uniform. So a uniform would be a set of data where nothing's more common than the rest. There's not kind of one big average. Everything's equally, likely across the whole set of data. You can also have bimodal. So bimodal is a set of data where there's actually two peaks. So two separate values that are really common. This could happen if your group has two separate distinct groups within it. One example is, between like unimodal and bimodal is if you go and do like average height, and maybe you go to a 7th grade class. If you just took all the boys and found the average height, you'd probably get unimodal because you'd have one average height amongst the 7th grade boys. But if you looked at 7th grade boys and 7th grade girls, well, because 7th grade, middle school, bodies are changing stuff, you get kind of those different height peaks where kids are growing at different rates and stuff. You probably would end up with two different peaks. You'd have an average height for the boys and an average height for the girls, because they're at different developmental stages. And those peaks would be, the two separate peaks would be two really common values, the most common height for the girls, the most common height for the guys. And because of those being separate, they would probably be different values, you end up with this two peak situation. So bimodal is going to be kind of two peaks like that. And you can even have multimodal. You could have something where there might be three distinct peaks. You look at you basically have more than two groups. You have three or even more groups that are distinctly like within your data set, and they're all different, kind of most common for their sets. So statisticians tend not to want to work with data that has multiple peaks. You don't really want to work with bimodal or trimodal. Their preferred method thing to do is to work with unimodal. So we want, unimodal is kind of the best because it's easy to understand. The math for it is pretty easy. It is also really common. It happens a lot. That's part of why it's so understood. There's a lot of situations where you end up with unimodal data. Uniform, again, it's not very common because in most sets of life, there's not like everything's the same. This is saying that all the values, small values, big values, middle values, they all get about the same amount. That's pretty uncommon. It can happen, but it's pretty uncommon. Bimodal, again, it's two distinct groups. And multimodal. So anything more than bimodal, we're going to say multimodal. You could call it trimodal for this, but it's multimodal. It's going to have more than two peaks. So when you look at data set, you can kind of get an idea what's going to happen by looking at it. So like, for example, the age of 500 college students. Should have an S there. That's going to be probably, unimodal, because you're going to have an average age. So most of your college students, traditional college students start at 18 and at 22. The average might be a little higher than, the middle of that, which is about 20. It might be more like 21, because you're going to have some students that take a year off before they start school. It might even be a little bit higher because you have some students that are much older before they start school. So you got those outliers that are kind of a little older. But overall average, you could have most of your students are going to be, a lot of students are going to be with that 18 to 22 range. lot of them are going to be probably around the 21 range compared to the few that you have that are much older than that. And you're going to have a few that are like 16, 17 because they're taking college classes, started early, but most of them are going to be in the middle range. This would probably be unimodal, somewhere between between 18 to 22. We'll have our one peak. And I don't know exactly where the peak's going to be. It's going to depend on, like I said, what's the highest in those groups. And those are all probably going to be bigger than like other ages. There's going to be a lot fewer 23-year-olds, a lot fewer 17-year-olds, even less 24 and 16-year-olds, and even less 25 and 15-year-olds. Maybe more on the high side than there are on the low side, but that's kind of what it's going to happen. So it's probably going to be unimodal. Here next one I have is age of 40 college employees. So this one I would argue that this is probably bimodal. The reason I'm thinking bimodal is because college employees includes both, the adult, like graduate, PhD, workers, as your faculty and staff who have, master's degrees and PhDs who have been out of college for at least 2 to 6 years before they got their degree, their PhD or their master's degree. And then they probably worked for a few years too. So they're going to be, more in their 30s, 40s, 50s. But you're also going to have all those college students because, right, we have our work studies. You get a lot of students that the first year after they get done with school, before they go off to go work somewhere else, they might work a year at the school still because they worked with people there, they liked it. So I would argue this one's probably bimodal. Because we have the recent grads or current students. That's kind of one group versus PhDs, older employees. And you can kind of break it into two groups. And if you can kind of see where you have two separate groups, this is probably the situation that's going to end up with a bimodal. That's kind of what's going to cause that versus unimodal when you can have one big group and you don't have like two distinct groups of reasonable size. So these are both going to be fairly big groups because you have a lot of PhDs working at college. Working as faculty and staff and administration, that kind of stuff. Last one here, I have a student ID number for 1,000 college students. Well, each college student gets a different ID number, so every ID number is going to show up exactly once. So this is going to be uniform. There's nothing that's going to be more common because there's not going to be one that's happened more than once. Each only one time. Anything you can think of where, there's no reason for any kind of peaks. It's all just going to be about the same amount the whole time. That's going to be uniform. And that can happen in real life too. You can have situations where levels don't change. It's just kind of stable. And it'll make it a uniform type of distribution. Another thing we talk about with graphs is their symmetry. So we call a distribution symmetric, or if it is left and right halves match. So you can draw a line right down the middle and the two sides match. If it's symmetric, mean, median, mode will all have the same value. They'll be right there in the middle, and they'll mean the same amount. With unimodal graphs, don't really worry about this with like bimodal, trimodal. We're just going to mostly work with unimodal graphs. We'll say if it's not symmetric, we'll say it's either left skewed or right skewed. And there are graphs we work with specifically that are right skewed or left skewed because they have uses, and we'll see those pop up. So a right skewed graph. Now I always get this backwards when I first started studying this. I always wanted the peaks to be where it talks about, but the skewedness is actually about where it's spread out. So a right skewed graph is actually skewed because the right side is more spread out. So you'll see the peak on the left, and then the right side, the right side tail will be longer. That's what makes it right skewed. People also call this positive skewed because it's skewed towards the positive to the right side. Left skewed is going to be skewed on the left side, and this is going to be considered negative skewed, skewed below. So here again, where it's spread out, that's the skewness. So left skewed, right skewed. So something that's right skewed, on the right side, it's going to be more spread out. You'll notice with this, the mean, median, mode are different values. Your mode is going to happen at the peak always. Mode is always at the peak, no matter what you're doing. The median, if it's right skewed data, will be skewed a little bit higher because you can have some higher values over here. So when you go to find your middle, you actually end up a little bit above the mode. And mean is going to be the most disturbed because, again, mode is disturbed the most by like outliers. So these values are way high out here compared to the low values. Those could be really disturbing the mean. Vice versa for the left side, so mean could be furthest left, then median, then mode. So again, peaks are mode. They're the most common. That's the highest point, so that's the most common value. That's what this is the most common value. For a symmetric graph, those are all the same, but not true for left skewed and right skewed. So down here, just want to tell us, you want us to say whether they're unimodal, and then if they are unimodal, whether they're symmetric left skewed or right skewed. First one is definitely unimodal. There's our peak, so there's definitely unimodal. There's only one peak on here. Because it's spread out over here, we would call that right skewed. So again, right skewed means the right side is more spread out. The left side drops off really harshly, the right side is spread out. This kind of happens in situations where there's some reason why one side might drop more than the others. So like an example why this would happen be, I think about like salaries at McDonald's. Because at McDonald's you have the minimum wage, right? No one makes lower than minimum wage. That's the lowest salary you can make. But then you also have people that have been there for a couple of years and they started making more than minimum wage because they've been there for enough years, they have experience, or maybe they got hired on with previous experience. You have people that start getting into like managerial positions, so they are making more because they're overseeing other workers. You have the store owners. You have all these people that are making maybe way more money than the basic workers. So with like McDonald's, you would have most of your values close to the bottom, and there's a cutoff where you can't be lower than that. But then you're going to have a few people, there's not very many compared to those bottoms, there's a few people making way more than those people at the bottom. There's no spread on the bottom because, again, that cutoff of the minimum wage, so this would be a situation. You might see right skewed or something like that, where there's kind of cutoff on one side and then it goes up. Another situation you might see this would be like credits. You kind of have, the least credits you can take is make a 0, but you can take lots of credits beyond that, right? Most people take between 12 to 15 credits per semester, maybe up to 18. But once you get past 18, 20, then it gets fewer and fewer and fewer. But there are still some people taking like 25 credits. There's some crazy people that do all that in one semester, and so that'd be more skewed out because you can have people going way high on that side, versus most people are going to be taking in the 12 to 15 range, with some people taking less. So you might see maybe a skewness right there because you have so much higher people that still be doing more. Symmetric, here this is weights of rugby players. A lot of like real life measurements like weights and heights, those will be symmetric, especially if you do a big enough group. So this is definitely symmetric. The two sides don't match exactly. If you like line these up, you might be able to find a little bit of variation. They're not much, but this is mostly the same. A little bit of variation is okay as long as you get that basic symmetric shape. This would be symmetric. And these are both unimodal, right? This is just the one peak, so this is unimodal. Last one here, you have two defined peaks, one there, one there. So this would be bimodal. Notice that they don't have to both be the exact same height. This one is the highest, so it would be the one biggest peak, but this one is a peak. It's clear that it goes down and it comes back up. Maybe this group is a little bit smaller portion of the total than this group is. That's why this peak's a little bit lower. We would still consider this bimodal. And we wouldn't worry about skewness on this or symmetric because this is a bimodal graph. We won't really worry about skewness, symmetry on unimodal graphs. Okay. Last page. Let's actually make ourselves a graph and we'll just figure out whether it's symmetric, left skewed, or right skewed. So let's draw a graph in here. I already put the bins down here. So we're going 60, 64, 68. When you're binning data like this, you gotta be careful about where you go if you're on the line. So 72 is right here. So you have to make a decision. Are you gonna put the data, in the next one up, or are you gonna go the next one below? And I think I'll do up. So 72 would end up in the 72 to 76 range. 80 will end up in the 80, 84 range. And if you're consistent, then you're good. So let's look at this. So between 60 and 64, I have nothing because my first value is 65. I do have one. I think maybe I should make a little table first. So, bin, and then the frequency. So between 60 and 64, that's 0. And between 64 and 68, I've got just 1. And the next row, between 68 and 72, I have 1. The next row, between 72 and 76, I have 1, 2. So 2. And between 76 and 80, I have 1, 2, 3. So 3. I think I'm looking. Trying to make sure I don't make my chart. I think if I go 1, 2, 4, 5, we're looking pretty good. We'll try that. So okay, so between 60 and 65, nothing. Between 64 and 68, we have 1. So I'll just do a bar like this. Between 68 and 72, there's just 1. because again, 72 we're going to put in this column. 72 and 75, both in this one, like this. 77, 78, 79, all go in this one, so we're going to go up to 3. All right, 80, 81, so I got 1, 2, 3, 4, 5 before I hit the 84, so that's going to all the way to here. And then 84, 85, 85, 87, I'm going to go in here, so that's 1, 2, 3, 4 in this column, so 4. And then 88, 89, 90, that's 3 in this one, so 3 here. And 93 is the only one that fits in this group. Okay, so that's our shape. You can see here that we do have pretty clear unimodal distribution. Got one peak at the top. And then you can see on the right side, from this peak it goes 1, 2, 3, it's done. On this side we go 1, 2, 3, 4. We have about 4 rows. It's a bit more spread out. We call this left skewed. There's more spread on this side than this here. It's kind of pushed together a little bit. So it's more spread out. And that makes that a unimodal distribution. Okay, last thing to mention in this section. So besides, the shape of the number of peaks and like which side is more spread out than the other, the last thing you think about with a set of data is its measure its variation. Variation describes how widely spread out the data is. The higher the variation, the more spread out it will be. And that will mean a low peak, because if you're spread out side to side, then your peak is going to be low. You're not going to have a lot of numbers in the middle because you're spread out. Versus if you have low variation, so you're clustered close together in the middle, then you have a high peak. So notice here, this is low variation. It's low because it's not spread out, and it has a high peak. Versus here we have high variation where it's really spread out side to side. It makes for a low peak. So you really want to pay attention to that. I get students all the time on the test or on homework get confused. They think high variation means a high peak. But no, high variation is spread out as a low peak versus low variation. Low variation is clustered close and has a high peak. So for example, which one would you expect to have more variation? The race times of the top 10 swimmers at the Olympics, or the race times of the top 10 swimmers at a high school swim meet? And why would that be? So if I look at the top 10 swimmers at the Olympics versus the swim meet, well, I think about it. The Olympics, usually these people have gone through trials and trials, right? They've had to beat other people in their country. They get here, they're the best of the best. They're going to probably be all about the same because they've all been working really hard for this. They've toned themselves as much as they can. Yeah, you every once in a while get one outlier maybe, but on average, the top 10 are probably get fairly close together. Versus you think about like a high school swim meet, and you have some people that have been doing it for years. They've been in it since like grade school. They swim all the time. They work really hard. They're almost like Olympic level. Like they're really good. And you get people like they just started this year. They've worked on it for a little bit, but they haven't been trying too hard, or like they've been trying hard, but they've only been doing it for a few months. It takes a while to develop the muscle and the toning and the experience. So I would say you probably expect, the high school to have more variation, more spread in your data because you have, less experience to more, and there's less of like this has been trimmed down. That you haven't like gone through all the people and said, wow, there's all these Olympic trials and stuff. You haven't done all that, so we expect more variation. We'll talk more about variation in the next section. Variation is a big thing to measure because once you know kind of where the middle each of that is, the measure of center, your median mode, then it's good to know also like how spread out it is, because if it's really low variation, all your values will be close to that median mode, and you kind of really have a good idea that they're going to be close. But sometimes you can have a lot of variation, really high variation. They're going to be spread out from that median mode. So once you know measure of center, the next thing to measure is how spread out your data is. Once you know those two values, you actually know almost everything we need to know about that set. It's variation and it's median mode, it's measure of center. So those are really powerful. We'll see how we can use those later on in this unit. That's it for today. I'll see you on the next one.